Hello, welcome to Fundamentals of Acoustics. Today is the last day of the current week, which is the 8th week. Yesterday we had developed an expression for T for a 3 media problem, and specifically we had defined T as the ratio of transmitted energy intensity to incident and intensity for the system. And the ratio which we had developed looked something like this. So, T equals 4R13 divided by R13 plus 1 whole square times 1 minus R23 minus 1 square times R12 minus 1 square divided by R13 plus 1 whole square sine square K2L. And R13 equals rho 3 C3 divided by rho 1 C1, R23 equals rho 3 C3 divided by rho 2 C2, and R12 equals rho 2 C2 divided by rho 1 C1. Now we will look at some special cases of this 3 media problem. So in a 3 media problem we have media 1, medium 2, medium 3, and the first case is, so we look at 2 special cases for starters. So in the first case we say that there is no medium 2. So then it becomes a 2 medium problem. If there is no medium 2, then the value of L becomes 0. So here there is no medium 2. Thus L equals 0. So if L equals 0, then I say that when L is equal to 0, then T is equal to T0, and this equals, in the numerator I still have 4R13 divided by R13 plus 1 whole square. Okay. Let us plot this. So on the x axis I am going to plot R13, on the y axis I am going to plot T, the value of T. As at x or at R1, when R13 is equal to 0, T is 0, and when R13 is extremely large, then once again T becomes 0. When R13 is very large, this denominator is approximately equal to R13 square, and that R13 square cancels with R13, so I have still left with R13 in the denominator. So the overall plot, it looks something like this, and this is an asymptotic curve, and it approaches the x axis at and it meets the x axis when R13 is infinite. So this is our TMax. So couple of things. T is equal to 0 when R13 equals 0. What does this mean? What it means is, when R13 is equal to 0, either rho 3 is 0 or C3 is 0, or rho 3 is 0 or C3 is 0. That is how we have defined R13. So either the air is very light, or the speed of sound in this air is extremely small. So either the air is very light or the speed, not speed of light, the speed of sound in the air. So speed of sound is what? P naught over rho naught gamma. So maybe the pressure in the air is extremely small, then also, but density could be reasonable, but if pressure is extremely small, then also it could be the case. So what happens in this case? So what that means is, so physically what happens? So when T is 0, it means that there is no energy entering the third medium. There is no energy entering the third medium, because T is the ratio of exiting energy and input energy. So what that means is that when in this portion, when either C3 or rho 3 is 0, then whatever energy comes to this interface, nothing gets out. One condition could be if pressure is 0. So if pressure is 0 or pressure is extremely small, then whatever fluctuations of pressure I have in media 2 at the interface, they will become 0 because of this continuity of pressure condition, right. So this type of a situation, so T is 0 when R13 is 0, so this type of a condition is known as perfect pressure relieving condition. What that means is that whatever is there, whatever pressure is there in the first medium, at the interface it gets relieved and it becomes 0. So that is the first condition. The other thing is that T is equal to 0 when R13 equals infinite. R13 becomes infinite. When does it happen? When either C3 becomes infinite or rho 3 becomes infinite. So either I have a very dense medium or C3 is infinite, which means the pressure in the system is extremely high. So what does that mean? That when some sound comes and it hits, it's essentially hitting like a rigid wall. So nothing gets transmitted to the second side. So this kind of a situation is called perfect rigid termination. It is rigid termination. So either you have a perfect relieving condition where pressure is extremely small, or you have a perfect rigid termination where P naught is extremely high. In both these cases, the transmitted energy to the system is 0. Now when you go back and look at some of the examples which we had done for open tube and a closed tube, what happens in a closed tube? You have perfect rigid termination. So no pressure gets conveyed to the outside world. Why? Because it is perfectly rigid, so there is no pressure going outside of the system. Similarly, in an open tube, it is perfect pressure relieving condition. So no sound energy theoretically leaks into the outside system, because there the overall P is 0. So this is the first situation related to this graph, that at when R13 equals 0 and when R13 is infinite, the transmission factor, it becomes 0. Now we look at the situation that what is the maximum value. So what is TMax? What is TMax? Now theoretically TMax cannot be what? More than 1, because whatever energy is coming, you cannot have more than energy getting transmitted back. So T is max when dt over d R13 equals 0. So I differentiate this relation, and what does that give me? So that gives me, it is 4 over R13 plus 1 whole square minus 8 R13 over R13 plus 1 cube. Okay. So, when I do the math, I find that Tmax occurs when R13 equals 1 and at R13 equals 1, T is equal to Tmax and its value is 1. Its value is 1. Okay. Because of this relation 4 R13, when R13 is 1, then it is numerator is 4, denominator is 4. Okay. So, what does that mean? What that means is, now this special case is a 2 media problem. So, what does that mean? That if you have 2 media, this is the boundary and R13 equals 1, it means that whatever sound energy is coming in, nothing is getting reflected back, nothing is getting reflected back, all of that energy is getting transmitted. R13 equals 1 means rho 3 C3 over rho 1 C1 equals 1, which means rho 3 C3 is equal to rho 1 C1. So, if there is medium 1, there is medium 2 and they can have their individually different densities and different values of velocities of sound, but if the product of these two entities for both media is same, then R13 will be equal to 1 and all the energy which is coming will get uniform, easily get, it will get easily transmitted. In electrical engine, so what is rho 3 C3? Rho 3 C3 is what? Its characteristic impedance of 3, right? And similarly, rho 1 C1 is characteristic impedance of media 1. And in electrical engineering, those of you who have an electrical background, you would recognize that when there is matching of impedance, then all the incident energy gets easily transmitted to the other direction. If the impedance does not match, then there is reflection and all the energy does not get transmitted. So, here the impedance of medium 1 and medium 2, they are matching. So, there is no problem in transmitting all the energy. Medium 1 or okay, medium, let us call this medium 3 for consistency. So, that is the case. Now, where would we like to use this kind of a situation? So, suppose you have a transducer and suppose there is this water or some fluid medium. So, this is fluid and this transducer is vibrating back and forth. So, it will emit some sound waves, it will emit some sound waves. Now, all of the energy which is emitted by this sound wave will not get transmitted to the fluid, because this is like a 2 medium problem. This energy will get transmitted to the fluid 100% only if rho 1 C1 for the transducer is same as rho 3 C3 of the medium. Okay. Now, a lot of times these transducers are made from quartz crystals, and for seawater applications, if I have to generate sound in sea, then this is rho 3 C3 corresponds to seawater. So, the quartz crystals impedance and the impedance of seawater, it does not match. So, what people do is, to make sure that they match, they put some rubber and they design the rubber in such a way, they design this rubber in such a way that its rho rubber times C rubber, it matches that of sea water. So, in that case the impedance matches and all the energy gets easily transmitted to sea water. So, this makes the transducer very efficient. These types of special rubbers are called rho C rubbers, because their material properties are designed in such a way to meet that of seawater. Okay. So, this is case 1, this is case 1. Now, let us look at case 2. So, what is case 2? In case 2, we will say that K2L is very small compared to 1. Where does K2L come? Okay, so first we will write down the expression for T one more time. So, T equals 4 R13 divided by R13 plus 1 whole square times 1 minus R23 square minus 1 R12 square minus 1 divided by R13 plus 1 whole square sin square K2L. Okay. So, K2L is coming in this term. When K2L is very small compared to 1, it means, what is K2? It is lambda 2 over, excuse me. So, K2 is 2 pi over lambda 2 times L is very small compared to L, which means that the length of the second medium is very small compared to 1/6 of lambda. So, if this condition is satisfied, then this term, it approximates, it does not approximate 0 when sin theta is very small. If I make it 0, then everything becomes 0. If sin theta is small, then this approximates K2, but this is sin square, so it becomes K2 square times L square. Okay. So, this is one thing. The second thing is that, so this is one assumption, simplifying assumption. The second assumption we make, so this term goes away, and the second assumption we make, so before we make the assumption, let me define it. So, in the 3 media problem, here what we have is that the width of this medium 2 is very small, in the sense that its length is very small compared to the 1/6 of the wavelength. The second thing is that rho 1 C1 and rho 3 C3 are same. So, what does that mean? That medium 1 and medium 3 are same. Okay. So, that is the second assumption. So, medium 1 and 3 are same, which means rho 1 C1 equals rho 3 C3. This is the second assumption. So, if that is the case, let us look at, so if that is the case, then what happens to all those R23, R12 and so on and so forth. So, R23 is equal to rho 3 C3 divided by rho 2 C2, rho 3 C3 divided by rho 2 C2, and the third assumption we make is, so at this stage we also assume that medium 2 So I am going to erase this right now because I will write it later. So I am making 3 assumptions. So medium 2 is very has very high characteristic impedance, okay, relative to medium 1 and medium 3. So what could be an example? So I could have an air here, I can have air here, and in between it could be wood, in between it could be wood. So in that case, so because of these 3 assumptions, I can write, so thus R23, which is the ratio of rho 3 C3 divided by rho 2 C2. So this is very small. This is very small compared to 1. R13, no, there is no R13. R12 is equal to what? Rho 2 C2 divided by rho 1 C1. So this is extremely large compared to 1, and R, is there R13? Huh? R13. So that is equal to 1. Okay. So 3 assumptions in case 2. One is the middle portion is very thin. Second thing is medium 1 is same as medium 2. Third thing is medium 1 and medium 2 are same, but they are not only same, medium 2 is very stiff compared to medium 1 and medium 2. So because of these assumptions, we get these approximations. So once we have done this, R13 equals 1, so this is 1. R13 equals 1, so I put 1 here. R13 equals 1, so I put 1 here. Sine square K2L can be approximated as K2 square L square. Okay. Now let us look at R23 minus R23 square minus 1. R23 is very small compared to 1. So this term I can omit. So I will be left with just minus 1. And the other one is R12 is very large compared to 1. So I can omit this term. Okay. So with these simplifications, I get T equals 4 divided by 4. I get 4 from here times 1 minus 1 R12 square divided by 4 K2L square. Okay. So 4 cancels out. So I get T equals 1 over 1, and this minus 1 and minus 1 becomes plus. So plus R12 square K2 square L square by 4. Okay. So T equals 1 over 1 plus, so R12 is what? Rho 2 C2 over rho 1 C1, and it is R12 square, so squares, and then there is a 4 in the denominator times K2. K2 is angular frequency divided by C2. Either you can write it as 2 pi over lambda or omega over C2, and it is omega square over C square times L square. So, this c square gets cancelled out. So, what I am left with is equal to 1 over 1 plus rho 2 L square omega square divided by 4 rho 1 C1 square. Now, what is rho 2 L? Rho 2 is the second medium, L is its width. So, what is this? Rho 2 L is equal to m, which is mass per unit area. Okay. So, this is equal to 1 over 1 plus m omega square divided by 4. What is rho 1 C1? So, this is medium 1, this is medium 3. So, this is z naught square m square. Yeah, okay. M square omega square by 4 z1 square. Okay. So, that is my, this relation is exactly the same as the relation which we had developed for velocity. If I take if I square the velocity on of the air in the earlier problem which I had addressed in this week, where you had a wall and we were interested in finding out the pressure as well as velocity at the transmitted end, then the velocity, if I square the relation for that and normalize it, I will get this expression. You should go back and check that. Okay. Now, I will define another parameter TL. So, TL is transmission loss, because what I am really interested in is how much energy is getting lost. So, transmission loss, and that is equal to 10 log of I incident divided by I reference minus 10 log of I transmitted by I reference. So, that equals log, and both all these things are based in I incident divided by I transmitted. Now, this ratio is inverse of T. T is I trans divided by I incident. Okay. So, TL is equal to 10 log of 10 . So, here there is this denominator. So, when I take the log of the inverse, this denominator will come up. So, this becomes 1 plus m omega by 2 z1 and whole square. Okay. And if I plot this curve on a board plot, so here I have log omega, this is in decibels. So, this is in, here the units are dB. Now, this has a low frequency asymptote and a high frequency asymptote. Low frequency asymptote means when omega is going to 0, the transmission loss is 0. So, it is like this, and high frequency asymptote is because of just this. So, it is a straight line like this, and the slope of this is 20 decibels per decade. Okay. Now, this equation for transmission loss is called limp mass law. it is called limb mass law. So, if your wall is rigid and it is not flexible so that it starts resonating, then this law works. And for limb, so this is the asymptotic response, and the actual response may be something like this. Okay. But in reality, walls are not perfectly rigid. So, at very low frequencies they behave as rigid masses, but as you increase the frequency they have their own resonances. So, when they have their own resonances, as I move on this positive slope line at resonance points, what may happen is, so initially the actual curve may be like this, but these may be related to resonances. So, at resonance the transmission loss becomes higher, at resonance transmission loss becomes higher, and then it keeps on going, and then you may see actually a dip. So, this is the actual non rigid region 2. What is red? Actual for rigid region. Okay. So, this is the real actual when it is non-rigid. So, at some frequency you will actually see a dip, and what this dip means is that at this frequency the energy which is getting lost is less, transmission loss has gone down. This corresponds to angular frequency known as omega coincidence. And we will not go into the mathematics of this, but what is omega coincidence? So, omega coincidence is equal to frequency coincidence times 2 pi. And what is frequency coincidence? This corresponds to frequency when wavelength it is wavelength of source wave. So, suppose you are exciting it by some frequency, at each frequency there will be some wavelength. So, this is the wavelength we are talking about. So, wavelength of source wave equals the wavelength of bending wave in structure. So, what does that mean? That when you are exciting it, structure will get excited and it may have some bending also. That bending will be associated with some bending wave, and for one frequency the wavelengths will match each other, and when that happens then you will have a dip in the transmission loss. So, your region 2 will not work well for reducing sound at coincidence frequencies. At resonance frequencies it will work very well, at other frequencies it will work moderately well, but at coincidence frequency it performs badly. So, that concludes the discussion for today, and we will meet next week. Till then, have a great weekend. Bye.